elastic sheet. So you can imagine a thin elastic sheet on top of a fluid, and we try to understand how the elastic sheet reacts to the motion of the fluid body. And this is my plan. So first, I want to talk about the background and motivation of the study, and then we move on to the mathematical description of the problem, and I'll say something about nonlinear Schrodinger equations and weakly nonlinear theory. And later on, I will say something about the fully nonlinear result, about two-dimensional problem and three-dimensional problem as well. And finally, I'll give some concluding remarks. And this is the joint work with Professor Paul Milevsky from University of Bath and Professor John Mark Vandenberg from UCL. Okay, before talking about the moving loads on ice sheet, I would say something about a very different problem. Well, they seem very different, but actually they are very closely connected. I'll show you. So before talking about, so first I will talk about a high-speed track, which is a facility called a high-speed test track. So all the aircrafts or weapons have to be tested before on ground before we put them into use. So there are two ways to test the aircrafts. The first way, the one way, is to use the shock nozzle. So you have a very long tube, and you fix the aircraft in the tube and blowing very strong air towards the aircraft, and then you measure the forcing, and you measure the temperature and deformation, etc., something like that. And another method, the other method is called the rocket sled. So the second method is called rocket sled. You tie which is a quite direct method. You tie the aircraft or the weapon to a very long track, and you move the aircraft with a very high speed using the rocket engine, and to gain very large speed, and then you test your aircraft. And if you Google on the internet, you Google the keyword rocket sled, you will find this item in the Wikipedia. And the world record for the second method for the rocket sled is 8.5 Mach number. So it's the 8.5 times the local speed of sound. So this is a world record. And the first, so if we focus on the rocket sled, so the second method, and the first questions to ask is the stability of the system, because you run the vehicles or run the airplane with a very fast speed on the track. So you have to be worried about the stability of the system. To study the stability of the system, we can build a very simple model. The model is called a Pasternak foundation model. So you have a point mass and moving with a constant speed v, and then you do the analysis on the forcing, and you use to model the system using the Newton's second law. So it's F equals ma, and ma is just the rho times and the position, the second derivative of the displacement. And then if you consider the forcing, if you study the forcing, you'll find that there are two restoring forcings. The first restoring forcing is you can model the track as a beam, elastic beam, and then the forcing of the deformation exerted by deformation of the sheet is proportional to the force derivative of the displacement. This is called Euler-Bernoulli beam, so it's a force derivative, and this term. And the second one is the ground, comes from the ground. And the deformation of the ground, you can imagine the ground is like a lot of springs. So the restoring forcing is proportional to the displacement itself. It's a Hooke's law. And then you can also have viscosity. You can also have something like buckling, so pre-stress. And you can imagine that the forcing of the mass is a sort of constant moving delta function, and you write down the equation, which is a linear equation and which is easy to solve. And you can solve this equation use the Fourier transform, right, and the inverse Fourier transform. And if you assume, if you neglect the viscosity, you neglect the buckling pre-stress, you can solve the system using Fourier transform, and you end up with a formula like this: y equals 1/2 pi, and for the inverse Fourier transform. if you focus on the denominator of the integral, there's something interesting. So if v is the moving, if you want to find the steady solution of the problem, and v is the velocity of the moving point, and if v is very small, then the denominator is always positive. You can take.
Excuse me, Dr. Wang. Excuse
Right.
me. The slide is not moving forward. Is it okay?
Which one?
The slide is not moving forward.
The slide is not moving forward.
The first slide is okay.
Which slide?
Your slide is only first slide. Is it okay?
No. I changed the.
Now it's changed, but
now it's changed.
Yeah.
So sorry. So
yes, now it's working.
Now it's working. Okay, so maybe
can you change it to the full screen?
So I changed to the full screen, but you mean the slide doesn't change?
Oh,
really? Does it work?
No, it doesn't work.
It doesn't work.
Yeah, I think it's okay. Yeah.
So maybe I go back to the.
Yeah. So sorry to interrupt you.
No, sorry. Thanks. Okay. So there are several ways to test aircraft or weapons, and so one way is to use the shock nozzle, and another way is just to use a rocket sled. And if you use a rocket sled, you are worried about the stability, and you can study the stability by just using very simple models, just Newton's second law and F equals ma. There are two restoring forces. One is the restoring force due to the bending of the elastic sheet, elastic beam, and the second forcing comes from the ground. The ground, you can imagine the ground is a spring, and then which obeys the Hooke's law. So you can write down the equations. It's just a linear equation with constant coefficients, and you can solve using the Fourier transform. And if you try to find a steady solution, you can end up with the equation with a solution like this. The red part is the integral, which we take the inverse Fourier transform. And if you take a look at the denominator of the integral, and you find something interesting, because when v is very small, the denominator is always positive, and you can take the inverse Fourier transform. You don't have to use the residue theorem. And if v is very large, then you can always find some k such that the denominator becomes 0. So there must be some critical v, such as the smallest v, such that the denominator could be 0, which is called the critical speed. And you can calculate the critical speed very easily. And when the velocity is very close to the critical speed, the denominator very close to the critical speed and slightly below the critical speed, the denominator could be very could be singular, so near singular, so could be 0, and the amplitude y becomes large when you take the inverse Fourier transform, and then the system becomes unstable. So you should avoid the critical speed due to the resonance between two forces. And you can calculate the critical speed if you substitute the numbers. For example, if you say, oh, the Young's modulus is 1,000 and the spring constant is 10, something like this, and you end up with the critical velocity is 360 kilometers per hour, which is pretty similar to the speed of the faster train in China or in Japan or in Europe. So it's quite reasonable speed. It's easy to reach. Okay, so this is a sort of example that is a totally different story, but I will go back to this example and show the main problem that we're gonna talk about is very similar to this problem in some sense, in the linear sense. Okay, so let's move on to the main problem that I want to talk about this today. So this is the we tried the main topic of this talk is we try to use the very large floating ice sheet as the transport link. So in fact, people know how to use a very large floating structure as a transport link for many years, for very long history. This is a graph cited from took from the Book of Squires in 1996. This is the Emperor of China on the move, held by a team of 8 people, and took from the Book of Squires. Squires' book summarized all the scientific book, moving loads on ice sheet, and his book summarized all the linear theories before 1996. So there's also many man-made floating structures. The most famous one is called a mega float. This is in Tokyo Bay in Japan, and this is a floating airport. It's quite large, so kilometers, several kilometers long. And the floating airport is an environmentally friendly system because it has less impact on environment than the land-based alternative. And this is a self-sustaining system because it can convert ocean waves into electricity for the energy supply for the airport. This is all man-made floating structures. And if you Google on the internet, you search for ice road truckers, the keywords, and you will find a TV show. The TV show is quite popular in the past few years. It demonstrates the use of frozen river and the sea as roads in Canadian and Alaskan and Antarctic during the winter for moving very heavy loads by trucks. So, but the show tells you, it's a TV show, tells you if you have to drive the truck very carefully. If you don't drive the truck very carefully, you will break the ice sometimes. So the figure on the left is a typical example of ice breaking, and the figure on the right is very interesting to me because there's a speed limit sign. It tells you are allowed to drive your truck between 10 to 25 kilometers per hour or 40 to 70 kilometers per hour. But you are not allowed to drive from 25 to 40 kilometers per hour, which is very weird. So usually we have a speed limit sign. You have a limit, you have upper bound and a lower bound. But it tells you there's something strange in between, in the middle. So 25 to 40, you are not allowed to drive. So this is a very, very interesting phenomenon, and we try to understand why this happens. And the real motivation of the problem is in the 1950s. So people wanted to explore the polar region. So the Antarctic exploration, the American military, this is just mostly of the military interest, wants to explore the Antarctic region. So they want to send people to the polar region. And the first question is, how can we land the airplanes? How can we find airport for the planes? And the natural idea to solve the problem is to use the very large floating ice sheets as the airport in the polar region, which is everywhere, right? And then, so the first question is that safe? Can we use the very large floating structures, very large ice sheet as the airport? So we try to understand if I land the airplane, or I'm moving the airplane with a constant speed, or I take off for the airplane takeoff, how is the vibration of the ice sheet? Okay, so the first person who worked on this seriously worked on this problem is called Wilson. He's a research at the University of Michigan, and he published his result in 1958. And he did a lot of experiments for aircraft landing, takeoff, and constant moving on ice sheets. And the first figure is the aircraft landing, and the middle one is the takeoff, and the last one is the constant moving. He found some strange things happening when for the aircraft to take off. So what he sees is there are 2 ways for the aircraft to take off, and as he said, all the takeoff records shows that all the double characteristics of the one shown in figure 14. This is figure 14. The second wave, there are two waves. The one wave is because of the weight of the aircraft, but the second wave comes from nowhere. So he said, the second wave cannot be a reflection from the show as it arrives much too early. The most logical explanation is as follows. It said, as the plane starts its takeoff wrong, it gains speed rapidly and passes through C min, generating a large wave, which then falls behind the forced wave that accompanies the plane. So he found a very magic speed, which he called the C min. He found some speed very strange. And if the plane passes through this speed, the system will gain a lot of will generate a large wave, which which propagates slower than the speed of the plane. That's what he discovered. He saw a localized, stable, large responses generated as a plane moving close to this critical speed. He found a very, very special speed with magic speed. And because of the existence of the magic speed, then people try to do more experiments to confirm his assertion. And there are two famous examples of two famous experiments. The first experiment was done by a New Zealand group in McMurdo Sound, led by Squire. And the second experiment was done in Lake Solomon by a Japanese team led by Takizawa in 1980s. And these two cases are quite different. So the first case is a deep water case. So the water depth is 350 meters. And the second case is a shallow water case because it's a 6.8 meters. And for the first case, the critical speed they found is 18 meters per second, which is quite easy to reach this speed. And the second magic speed for the shallow water, the magic speed is 6.1 meters per second. So first, let's take a look at the first deep water scenario experiment. And the critical speed is 18 meters per second. If you see that, so if the speed from A to E, the amplitude as the speed is increasing, but the speed is smaller than 18 meters per second, less than the critical speed. As the speed increases, the amplitude increases. But when the speed is bigger than the critical speed, the amplitude decreases as the speed increases. So that's what they observed. And if you go to the shallow water scenario, and you will see the experiments, and as amplitude increases, and the critical speed is 6.1, and the first figure is 2.2, and the 4.2, and the 50.5, 5.5, and as the speed increases, amplitude increases. But after 6.1, as the speed increases, the amplitude decreases very quickly. So this figure shows clearly the amplitude versus the speed. So you will see there's a critical speed 6.1, where the amplitude reaches maximum. And after that, the amplitude decreases. So if you take a look at this figure as a speed of 5.5, and you will see some wave like solitary waves. So you have a very large solitary pulse in the middle, and you see also very small oscillations which decay to zero in the far field, which is in nonlinear wave. In the context of nonlinear wave, this is called a wave packet of solitary waves. And okay, so this is the experiment, and then we try to explain this experiment by theory and numerics. So we start with the mathematical description of the problem, and which is quite I think everyone knows the mathematical description. So we assume the fluid is inviscid and compressible, and the flow is irrotational. So the motion of the fluid body is governed by the Laplace equation, and there are two boundary conditions. One is the kinematic boundary condition, and the other is the dynamic boundary condition, which is also the Bernoulli equation or pressure equation. And there are two restoring forces. One is due to the gravity, and the other one is due to the elastic bending. We use the simplest nonlinear model for the elastic bending, which is called the Kirchhoff-Love model. It's the second derivative of the curvature, and also there are external applied forcing to the system. And then, so first we focus on the linear theory. We assume the fluid is of infinite depth, and the pressure is a point, is a delta function, and the delta function moves with a constant velocity u. And then you can linearize the system and solve the system using the Fourier transform, and you can end up with an integral. And well, surprisingly, the same thing happens as a faster track, because if you focus on the denominator, if u is very small, the moving load is small, then the denominator is always positive. Then you can always take the Fourier inverse transform. And if u becomes large, then you will find some k such that the denominator becomes 0. And then you have to use the residue theorem, something like that. And there must be a critical speed u, the smallest u, such that the denominator could become 0. And if the speed is close to the critical speed, then the displacement theta, it could be very large. Okay, so that's the linear theory. And now we assume the velocity, the moving velocity, is very close, slightly below the critical speed, C min, and very close to C min. And we can using the residue theorem, we can find the approximation of the solution. And the approximation of the solution is quite interesting, because the solution is there is a faster part of the solution, so a faster rapidly changing part, which is a carrier wave with a constant wave number, and moving with the phase velocity u. And there is also an envelope. The envelope is a decay to 0, it's exponential decay envelope, and the envelope also moving with the speed u, but as a group velocity. And the envelope is much longer than the carrier wave, because C min minus u is very close to 0. So there's epsilon in the envelope. So envelope is very long. And if we see the amplitude is also very large, because the C min minus u is very small, and in the denominator, the amplitude is very large. So that's what the solution look like. So you have a very long envelope, it decay to 0 in the far field, and a very fast carrier wave. And this point is the velocity, the group velocity is equal to the phase velocity near the critical speed, and the solution, because of group velocity, is equal to the phase velocity. So this point, C min, is non-dispersive point. The dispersion is very weak. Dispersive effect is very weak, and the amplitude, and there's some physical behind this solution, because when u is very close to C min, because the group velocity is equal to the phase velocity, which is also equal to the moving load, the speed of the moving load, then the speed of the moving load, the loads give energy, inject energy to the system, and all the energy are very fully localized, because it cannot propagate away from the pressure. So the energy accumulates within the very small regime. And as energy accumulates, the amplitude increases. As an amplitude increases, becomes very large, and the nonlinear phenomena has to be incorporated into the system. So the linear theory fails near this critical point. So the linear theory does not work if you focus on the resonance, this critical point, which is also called the resonant point, because waves start to resonate and the amplitude becomes very large. You have to take into the, you have to consider the nonlinear effects. So if you start to consider nonlinear effect, we start with a weakly nonlinear theory. So you take motivated by the linear solution, you take a carrier wave, which is a cosine or sine, is a sinusoidal wave, and you multiply by a very slow small amplitude, slow varying envelope. The envelope is much longer than the faster varying carrier wave. And then you have small parameters, and you substitute in this ends us into the hydroelastic wave problem that you're going to solve, and you start to do asymptotic analysis. You do Taylor expansion, and you will end up with a nonlinear Schrodinger equation for the dynamics of the envelope. And this is quite a standard argument. And there are two constants in the nonlinear Schrodinger equation. One is called the Stokes nonlinearity, mu, and another one is just the linear dispersion coefficient. And the combination of these two coefficients are important. If the product of lambda and mu is negative, then the NLS is in the Benjamin is called focusing NLS, and the carrier wave is in the Benjamin Fair unstable regime, and you will have bright solitary wave solutions, which decays to 0 in the far field. And if lambda times mu is positive, then the wave, the NLS is called defocusing NLS, and you only have you only have dark solitary waves. You don't have solutions decays to 0 in the far field. You only have dark solid which approach a constant in the far field, decay to 0 in the middle. And so if you want to see from the weakly nonlinear theory, if we want to find the wave packed solitary as you observed in the experiments, if you want to find the solutions as you observed in the experiment, you have a pulse in the middle and with oscillator decaying tails in the far field. You need two conditions. One condition is you need some point which is non-dispersive, where the group velocity is equal to the phase velocity. And the second condition is the NLS at this particular point should be focusing. You have solution decay to 0 in the far field. And that's the condition for the existence of wave packed solitary waves. And the first group who was working on the hydroelastic wave, nonlinear hydroelastic wave is Emilian Peru and Fedra Diaz. Emilian is in the audience. And they carried out the normal form analysis. They derive the nonlinear Schrodinger equation for the fracture gravity waves. And they found that there is a critical depth HC. So if the fluid is shallower than is smaller than HC, then the NLS is focusing. And the wave amplitude solitary waves can be expected. Wave packed solitary can be expected, and as observed in the experiments. However, if the fluid is very deep, if the depth of the fluid is bigger than HC, then the NLS is defocusing. And the NLS analysis, the weakly nonlinear theory, fails to predict the existence of small amplitude wave packed solitary waves. However, as we see in the experiment done by the New Zealand group, they do observe wave packed solitary waves. They do observe these kind of solutions in the experiment, but the weakly nonlinear theory doesn't apply to this experiment. So we have to go back to the primitive equation. We have to go back to the fully nonlinear system to see whether we can find these solutions in the fully nonlinear system or not. And okay, so let's move on to the fully nonlinear theory, fully nonlinear numeric experiments. And the numeric experiment is it's not difficult, right? So there are not a lot of excellent numerical scheme for two-dimensional water wave problems. And here we use a conformal map, which is pretty easy to do. I don't want to go to the details of the conformal map. And you end up with a very simple integral differential equation if you want to find traveling wave solutions. Just integral differential equation, a single equation, and you use Newton's method to solve this system. And I just want to show you the result in 3 slides. And so first, let's forget about forcing. So the first question: can we find the wave packed solitary waves in the free system? So without forcing, can we find such kind of solutions? The answer is yes. We can find these solutions in the fully nonlinear equation, so which is features a big trough in the middle, or solitary pulse in the middle, and the oscillatory decaying tails in the far field. And surprisingly, this solution doesn't bifurcate from 0 amplitude. this solution bifurcates from a solution called generalized solitary waves. Generalized solitary is a non-physical solution. You have a pulse in the middle, and you have non-decaying oscillations, a train of ripples in the far field, Stokes waves in the far field, and but mathematically it exists. So the bright solitary waves bifurcate from generalized solitary waves, and the generalized solitary bifurcates from periodic waves, and the periodic waves bifurcate from zero amplitude. That's the bifurcation mechanism, which is quite funny. So this is SW is the solitary wave, bright solitary, and GSW is a generalized solitary wave, and PW is a periodic wave. So the bifurcation is the free without forcing is something like is a curve in red. So this is a speed, as a horizontal coordinate speed, and vertical coordinate is the amplitude. And now we add a forcing. We add a forcing to the system. We want to see what's going to happen with forcing, the system with forcing. And let's say something about a famous problem. So you apply forcing. You have a boat. If you have a boat moving on a shallow fluid, what's going to happen? So for shallow waterways, you also have a bifurcation without forcing. So there's a critical speed, which is called the square root of GH, right? Square root of GH is a critical speed, and the solitary waves only exist above this square root of GH. And below square root of GH, you have periodic waves, it's a linear wave. So I normalize square root of GH as 1 to be 1, and below this is a supercritical bifurcation, and below 1 you have linear waves, and above 1 you have solitary waves, free solitary waves. And now you add a forcing to the system, and you add a bolt to the on the surface, and then moving the forcing with constant speed, and you try to find a steady solution. And because you add a forcing to the system, you break the symmetry of bifurcation. Now you have two branches. And one branch is the upper branch is a small perturbation of free solitary waves, free solitons, and small perturbation of free solitons. And the lower branch is a small perturbation of free stream, so just the ripples. And okay, so there is a gap between the steady forced solution and the bifurcation point, which is called the transcritical regime. In the transcritical regime, there's no steady solutions with forcing, and there's no steady solution for the linear waves. The only solution exists in the transcritical regime is the solitary waves, free solitary waves. So now the question is, if you apply the forcing in the transcritical, you apply the forcing and apply the boat, you add a boat to the system, and you're moving the boat with the speed in the transcritical regime. What's going to happen? You will never see the steady state because all the steady solutions are on the right, and you don't have the linear mechanism to radiate energy, radiate waves away from the forcing, because all the linear solutions are in the supercritical case, in the supercritical regime. All the solutions in the transcritical regime is the solitary waves. So if you apply forcing and moving the forcing in the transcritical regime, what you see is the periodic shedding of solitary waves, and use a nonlinear mechanism to radiate energy. And this solitary will propagate faster than the speed of the boat, and you will see this generalized solitary waves ahead of you. So and this wave runs faster, so it propagates away the energy. The system get rid of the energy. So that's a quite famous problem for the shallow water scenario. And let's go back to our problem, which is quite different. So our problem is different because the bifurcation is different. So now you have a bifurcation, which is a subcritical bifurcation, but there's also something in the supercritical part. And if you apply the forcing to the system, you try to find a steady solution with forcing, and you will find something weird. So if the forcing is small, you don't have transcritical regime. All the solutions can reach the bifurcation point. This is the bifurcation point. You don't have transcritical regime. But if you add larger forcing to the system, you will have a transcritical regime. In the transcritical regime, as the shallow water case, there's no solutions, no linear solutions, and no steady solutions with forcing. The only solution exists in the transcritical regime is the free solitary waves. So if you apply the forcing and moving the forcing in the transcritical regime, you will see the generation of large amplitude solitary waves. And these solitary waves propagate slower than the forcing. And that's why Wilson saw some solutions, all the double characteristics of the takeoff record. And what he see is the two waves and the generator wave falls behind the airplane. So okay, so that's explaining his observations. And we can also do direct numerical simulations, time-dependent simulations. If you add a small forcing to the system, you will just see ripples. You don't have any, you will not see any larger responses. And if you add large forcing in the transcritical regime, you will see the very large amplitude of solitary generated. And if you turn off the forcing, and then these solitary waves can exist, coexist with the sea surface state, and the propagate is a stable state, stable solitary wave that propagate for very long distance, and it will break sometimes when the ice sheet becomes very thin. So that's the direct numerical simulations. And finally, I will say something about the dark solitary waves, because in deep water for hydroelastic waves, the NLS is in the defocusing NLS. It's a defocusing NLS. So defocusing NLS predicts the existence of dark solitary waves. So you will, the question is, can we find the dark solitary wave in the full Euler equations? The answer is yes, you can find dark solitary waves in the full Euler equations, and the bifurcation is also very similar to the bifurcation of the bright solitary waves, because it bifurcates from the minimum of the phase speed, the critical speed, and then it exists in the supercritical case, and there is a turning point for the dark solitary waves. And the dark solitary, when it turns around back to the supercritical regime, and the dark solitary waves will become bright solitary waves, and will first become generalized solitary wave, and then becomes a dark bright solitary waves. But this dark bright solitary features two depression waves placed side by side. So that's the global bifurcation of the dark solitary waves. So okay, so so maybe I don't have time to go further. So I'll say something about my recent work. Recently, I worked on I found this is a very weird bifurcation, never happens in before. So this bifurcation is quite interesting. So the bright solitary wave doesn't bifurcate from zero amplitude, bifurcate from generalized solitary waves, and generalized solitary waves bifurcate from periodic waves. And also the system can guarantee can support the dark solitary in the system. And once you have one example, you have more examples. So recently I found more. This bifurcation method is quite universal, I found, and I can find a lot of examples of this, which fluid system which can support this weird bifurcation structure. And one example is the interfacial capillary gravity waves, when the density ratio of the upper layer to the lower layer is large. This picture is a density ratio 0.4. So I found these structures. I can compute all this, the global bifurcations. And I also found this bifurcation structure in many other fluid systems. For example, the capillary gravity waves of a conducting fluid under normal electric field, or interfacial waves on the horizontal electric field, or with constant vorticity. And the question is, does this new bifurcation exist in other scientific contexts, for example, physics or biology or chemistry? And the second question, what is the ad hoc model? Because the shallow water, there's a KdV solitary wave, you can have KdV equation, right? You can soliton, you can have KdV equation, and the wave packet solitary wave, you can have NLS equation. And what is the bifurcation? What is ad hoc model for the new bifurcation? What is a phenomenological model for the new bifurcation? So I proposed a new model, which is sort of a kind of wooden equation. And I add some complicated nonlinearity, and then I can find all the bright solitary waves, generalized solitary, dark solitary waves, and the periodic waves in this using this reduced model, using this ad hoc model. And I can find that for the small forcing, there's no transcritical regime. For larger forcing, you can have transcritical regime. This model describes the system very well. So that's the end of the story. I have to finish my talk. Thanks for your attention.
Thank you very much. Thank you very much, Dr. Wang, for very well organized the talk and very interesting presentation. Thank you very much.
Thank you.
Okay, now let's open questions and comments. Okay. Do you have any questions?
Hi, Zhan.
Hi, Emine.
So the model equations you have is for non-forced waves, yeah?
I can also add a forcing. So I for the model equation, I also add a forcing to the system, and it shows the same behavior as the Euler equations.
Okay, that's my question. So if
the radical curve is the larger forcing, and the green one is the small forcing.
Yeah. Okay. That's my question. So
okay,
you can do it.
Thanks.
Okay. Any other questions? Okay, so in this figure, it's may I understand is that generalized solitary waves are unstable?
I don't know. I'm not sure. I haven't tested the stability of generalized solitary because this solution is I have to say this solution is I cheat a little bit because when I compute these solutions, I use periodic boundary conditions. So this is not real.
Okay.
Because you see, I add some red dashed curve on the tail, right? So I can compute these solutions with even larger domain. Then you will see as a smaller domain, the solution for the blue one is just on the top of the red one. So that means you can always add periodic solutions to the solution. That's how I prove this is a generalized solitary wave. But we cannot actually, because the computational domain is always finite. So you cannot really get real generalized solitary waves by computing, right? So that's one problem. And I guess the system is unstable because I never see any solution, any periodic solution is stable.
I see.
Because you see in the train of ripples. So the train of the ripples is sort of is the periodic wave, so the Stokes wave. So I think it should be unstable, subject to subharmonic perturbation or superharmonic perturbation, somehow like that. That's what I guess, right? I don't know. I never checked that.
Okay. Thank you very much.
I have a question.
Yes,
Yes, please.
Hi.
What kind of continuation method did you use?
Oh, I use numerical continuation method. So you have to choose some bifurcation parameters, right? So you can use speed as a bifurcation parameter, but that's not that doesn't work for the turning point. So for the turning point, you have to use the amplitude of the wave as the bifurcation parameter, then to continue the curve. So you can alternatively using speed or amplitude as a bifurcation parameter to continue the curve.
Okay, and if we look at this, the red curve on the right side, the left one, in the left one.
The left one.
in the left figure, if we look at the, I think it's a pink curve, right?
Pink curve. Okay.
Yeah, I think it is stopped, right? What happened? What happened there?
No. You can continue this curve.
Okay. So
I didn't show that. Well, I just finished this quite recently, so I didn't explore very roughly. So I can continue this curve, and you continue this curve, the same thing as this bifurcation happens. So it's pretty much similar like this.
okay, I see. Yeah, thank you. Yeah.
So it's a dark solitary wave is a bifurcation curve like this. I just didn't continue the model equation, but you can always do that.
Yeah, okay. I was just curious. Yeah.
Okay, thanks. It's my fault.
Okay, thank you very much. Any other questions? Okay, thank you very much again, Dr. Wang.
Okay. Thank you, Zhan.
Thank you very much for your contribution. I really
Thanks.
appreciate it. Okay.
Thanks.
Okay, thank you very much, everyone, for taking the time to join this seminar. Today's seminar is now closed. Thank you very much again. The next seminar will be held on September 10th. Okay, I'm looking forward to seeing you again. Thank you very much.
Okay, thank you, Zhan.
Thank you,
Thank
Zhan.
you, everyone.
Bye, Zhan.
David,
Hi, Emily.
Thank you very much.
Hi.
See ya.
David, Dr. Lance.
Yes, thank you very much for
Thank you very much.
I had problem with my micro.
Hi, Evelyn.
Thank you very much for joining us.
Yeah, sure. Good night.
Good night. Thank you.
See ya.
Bye.
Okay.